Hi guys, today I want to go on with the presentation of the hardware engineer magnetics inductor know-how, and we have done the first and the second problem, as well the third, which was the inductor. The third was also the hysteresis plot. We performed on LTspice this simulation here, and then we have to answer to all of these questions. And of course I will be fast because I don't have the time, and also I don't want to do again all over again the exam of physics. But then we have the hardware engineer magnetics transformers know-how. Here again we have to say to which type does this curve belongs, and then this question is quite hard. So it is impossible. This question is impossible to answer unless you haven't worked with transformers, okay? So this is impossible. This is too much for a candidate, in my opinion. Let me know in the comments if you have reached this level in power electronic design, but for me, for a candidate at least, this is too much, okay? And then we have the isolated topology know-how, and here we have to say what these are, basically, what these waveforms are. And then we have to also to study the transfer function of this push-pull. And finally, we have two waveforms, and we have to say in which types of converter does this waveform belongs. I think it's quite easy to understand, but we can verify very easily with LTspice. Okay. So let's start with all these questions here. So I will take the screenshot and let's put it on Paint so that we can give a very fast motivation. So let's start with the first question. The iron powered cores have higher core losses than ferrites. So basically here you have to know the formulas, and they are very basic formulas. So for the first one, you have to know that the power loss, the loss of the core, is basically proportional to the b square times f square times the frequency. And then the iron powered magnetic the iron powered has greater current losses than ferrites. This is true. Let me put a bigger size, please. Okay, second, the iron powder core have higher winding losses than ferrites. Result in higher winding losses. Okay, this is not true because the losses on the wire, P wire, are basically proportional or equal to I square times RAC. And they depend on the wire, okay, not on the core. So they are not influenced by the type of the core. So the iron powered magnetic core typically result in higher winding losses. No, because winding losses generally have more power because they depends on I square, and in a transformer I is okay. So it's not accurate to say that core losses is higher than winding losses. I don't actually absolutely I don't think so. So this is true, but this is false. Okay. The leakage inductance, LS of the transformer, is frequency dependent, and it has different LS characteristic if Litz wire is used instead of solid round wire. First we have to understand what the Litz wire is. The Litz wire is basically, so this Litz wire here is basically an integrated wire I don't know if I can draw it correctly, but it is something like this. My drawing is I think my drawing is horrible. So let's search Litz wire. You can understand immediately. Okay, it is Italian, but I think that you can understand perfectly by the figure what a Litz wire is. Okay, and so the Litz wire is designed to reduce the skin effect, basically. So the leakage inductance is frequency dependent. It is true because the leakage inductance has an equation like mu0 mu r times n square times h, the area, over L. Let me go higher. Times some factor like 1 minus k, something like that. K of f. Okay, and this frequency is, in this k, is frequency dependent. It's a design parameter, and it is a frequency dependent. And so this is true. It is frequency dependent, and the Litz wire, since the Litz wire modifies the skin effect, and the skin effect is frequency dependent, when the Litz wire is used, the leakage inductance is indeed modified. Yes. So the tree is true. True, false, true. Then, in order to keep the same RAC, RDC ratio of the transformer winding at higher frequency, the product of operating switching frequency, winding width, and Litz wire should be kept constant. The proportion, okay, so here the proportion of the RAC over RDC is indeed proportional to the frequency. So frequency times W times D must be held constant. This is true. Five. The bunched bundle diameter of the Litz wire dominating affects the amount of proximity effect losses in winding. Okay, as I said before, the Litz wire is designed to keep as many to reduce as many losses as possible. Okay, so the diameter of the Litz wire, let me write it down here. The proximity losses, let's call it P prox, are proportional to the diameter of the bundle to the square times the frequency of the system square times the magnetic field B of square. Yes, it's not magnetic field, it's H equal to mu 0 times B, etc. But you got the picture. So basically, the losses of the proximity effect, they grow up with the diameter. So dominant affects the amount of the proximity effect losses in the winding is true because the proximity effect is proportional to the diameter. Then 6. Dominant component of the core losses in high frequency right comes from eddy current losses. This is false. Because no, this is false. But if you need the because in high frequency, the key here is high frequency losses. Okay. So if you need if you don't trust me, but you need the formula, I can give it to you. So basically here, the eddy, the losses of the eddy currents. Yes, I did some research. The losses of the eddy currents are proportional to B square, F square, and D square. Okay. And the hysteresis current, the hysteresis losses, P hysteresis, are proportional to the frequency times B square. So the hysteresis losses they dominate at low frequency. Okay. Ah, wait. Let me read. No, no, no. Sorry, 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 sorry. Sorry, sorry, sorry. I read it wrong. I read it wrong. Let me reread again. Dominant component of the core losses in high frequency writes comes from eddy currents and not from the hysteresis. Ah, no, 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 no. This is true. Sorry, sorry, sorry. This is true because the eddy currents they have frequency square, and the core losses do not have the frequency square. Yes, the core losses, the parasite losses grows with f square. So I think that also this is true. Then we have also the what was that? We have also the 8, which statement is correct, multiple non-shop are allowed. So let's take also all of this and let's go to the next. Let's go here. Okay, so again, these are other questions. So first, the magnetic properties of iron power make it a good choice for many inductor application, but it's not a good choice for main switching transformers. So the iron power cores, so iron power, the switching application, generally speaking, when you have a switching frequency of 100 kilohertz, for instance, generally speaking, you use ferrite, okay, ferrite. So iron power for switching transformers, let's just say that the iron power have high losses. They have very high losses. They have very high losses due to the eddy currents. And if the answer is so, if the answer is for high frequency transformer, this is true. Okay. If for the main switching transformer, if he intends for a high frequency transformer, this is true. So ion power is not a good choice. Not a good choice for the main switching transformer. Okay. Industrial application meaning 100 hertz basically, but not for high frequency transformer. Second, so this is true. Okay. Ferrite materials have higher resistivity than power data materials, which permits them to operate more efficiently at a higher frequency. Yes, this is true. There is nothing to say. The resistivity, the resistivity. Remember that the power of the eddy currents is proportional to 1 over the resistivity. Okay, so if the resistivity is lower, the sorry, I beg your pardon. If the resistivity is higher, the losses are lower. Okay, so this is true. If the frequency of the voltage first harmonic is less than 10 kHz, there is no need to use the Litz wire in the transformer. True, because the skin effect, sigma, is proportional to 1 over radical square of f. You have to remember this. Okay? And this is negligible. This is negligible when frequency is less than 10 kilohertz. So this is true. And the lead square is not necessary. Then, the higher the frequency, the higher the current density in the center of wire. False. Because the higher the frequency and the higher the current density in the center of wire. No, because there is the skin effect. The skin effect, let me write here. So, skin effect forces current to the surface. Meaning that current density decreases in the wire center at higher frequency. Let me put, no way. Don't tell me that I can't, I really can't increase the size. Ah, yes, I can. Okay. Thanks. Okay, so this is the answer to number 4, which is false. This is true. Skin effect forces current to the surface, which is equal to current density decreases in the wire center at higher frequency, because the current density J is proportional to 1 over the skin effect. Well, of course, it is to be expected, no? If the skin effect, sorry, guys, okay, if the skin effect, if you have a current, no? And you have current flowing to the center, if you have higher frequency, the skin effect will force the current to distribute over the skin. So over here, if you can color in red, green, and etc., the red will be on the board. I imagine the orange will be there. Okay, and imagine that the yellow will be like this, and the green will be at the center. So it is something like that. So if I write skin effect on Google, you will immediately see. Okay, so it is. I think that it's quite exactly like this. Yeah, as you can see, this. Oh, this is beautiful. Oh yes, this is beautiful. Let me click on this. Why there is a skull here? Okay, so this is perfect, guys. Remember this photo, and you will understand everything. Let me put on my paint. Splash. This is far better. So now you have proof that when you are in the low frequency, the skin effect is negligible. So I was right. And when you are in the higher frequency, the current density tends to have a great impact on the skin. This is what is the information that you can? This has a lot of application, okay, in electronics, but also an important application in your real life. If you take the current, so this is you, okay, let's just say that you take the current from your laundry, okay. Unfortunately, you don't have the connection to ground, unfortunately, and you take the current. The current in your body, since the grid of your palace is an AC, 12 and 20 volts, okay, 50 hertz. Basically the current will basically go in your skin, most of your current density. So meaning that you will leave your heart basically almost unscathed. Okay, so not so much, because then the current will also go through your heart, but your skin will be mostly damaged by this, and your organ and your muscles will be less damaged. Let's just say that. Okay, let's just say that. But of course, since it is low frequency, don't expect to save your don't expect to be saved for this, because again, you are in the low frequency, so don't expect to be saved. Okay. But by the way, so yes, these are my 3D drawing. As you can see, they have not evolved over the year. By the way, let's continue with this question. The air gaps in high frequency transformers and inductors are used only if there is the DC bias. What? Why? No, that are used also in SE or as well. So this is stupid. Okay. Air gaps. By introducing a concentrated discrete air gap to the transformer core, we can decrease the proximity and the fringing losses. However, the MC profile might get worse. Yes, yes. This is true. Because when you introduce the gap, so basically, when you have a transformer like this, okay, in the border here, so let me zoom this part. In the border here, some of the field will not go straight like this, but will leak like this. This leakage of the flux is called fringing effect. Not only this, but this fringing effect can even couple to the magnetic layers that you have there, and this will reduce EMC. This will reduce a lot of EMC. If you have planar transformers, for instance, where you have the metal here, and you have all the PCB like this, all the layers like this, the fringing effect on the board can latch to the layer like this, and this will not only create losses as well, but also EMC problems. I can type on Google again fringing effect. You will see exactly what I mean. And I don't know if there is some EMC test, but the air gap creates this fringing effect, which can derange the effect of your MC. Okay, so you have to take also in account that. So this is true. 7. The era product of the geometry KJ are well-known methods for the design magnetics. Yes, this is nothing to say. Current density of J can be seen as a reasonable value during transformer inductor design. Yes. There are some. There is nothing to say here. This is just. If you search paper, you will find it. Okay. But by the way, what we can say here is that the conductor loss P is equal to J square times the resistivity rho. So if you have sorry, not times rho, not the resistivity. But if you have this value here, is approximately good value, reasonable value during this design because it matches the balances the conductor losses of this. Okay. So let's go on to this. We have to understand which of this type this converter does belong to. Let us go on with the lesson here. Let's go here. To which type the converter belongs figure A1 and A2. Okay, basically A1 belongs to any kind of converter which operates in a single quadrant. Okay, so the first A1 belongs to basically a forward, because the forward operates in the first quadrant, and the second A2 belongs to a flyback because it has the air gap. So the first is not air gap, and the second is with the air gap because you have the increased area. You have the increased area to store and increase also the saturation. You have increased the current for the saturation. As you remember, when the LG increases, you can, if LG goes up, Ni, meaning H, goes up, meaning that I, the maximum I, goes up. So, meaning that having LG, higher LG, meaning that you can store more current I before saturation. Okay? So, and since flyback converters operates with the gapped inductor, this is the flyback, of course, the flyback and the forward. You can, by the way, verify with this test bench that I gave you to you, basically by giving not a sign, okay, but you can give also a square wave between 0 and, I don't know, a positive value, like this, with a T rise of 10 micro, something like this, T on 1 micro, and T period, and T period 2 micro, something like this. If you press run, of course you have to rescale it. Ah, okay. Oh, fantastic. It's bugged. Fantastic. Ah, okay. No, it was not bugged because basically it was the transit was not enough, so it was not a bug. So basically you have to put between 0 0.5. The T on period is 1 over Fs, and the T on, let's just say that you have uh, 0.5 over Fs. Rise and fall of 1 micro, something like this. And the switching frequency, let's just say 100 kilohertz. So you have a square wave, okay, like any other that you can find on the DC-DC converter. And as you can see here, I do only have just the positive waveform, okay, and it is assumed, it is correct to assume this because, well, if I repeat the cycle even for 5 times, you will see that I will never go in the negative part. And this is true with forward converter because if you draw even flyback converter, let's draw the flyback. The flyback converter, it is done like this. Forget the yes, you can put the diode and the clamping guy here, blah 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 blah. But I don't care. Okay. Yes, you don't put the thing here. No, 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 no. Yes, let's neglect that for a bit. I do remember that the dot should be like this, if I remember, but let's skip this. Okay. The thing here is that this transformer will not go in the other quadrants because let's take the flyback. For instance, I opened the first flyback that I had on that I found on the on my computer. Okay, I can neglect I neglect everything. I neglect this. Neglect a lot of things. I neglect everything here. Okay, just a normal flyback, which k equal to L1 L2 equal to 1. I honestly don't care. Okay, let me put just the magnetizing inductance because this is important of 10 micro, something like this. Neglect the shunt, neglect everything, the most basic flyback on earth. Okay, so that's something like that. Let's run the simulation. I honestly don't care. What I do care, though, is the voltage across the inductor, and also the current across it. So as you can see, this is the primary current across the inductor, and it never goes negative. Yes, aside from this, but it mostly stays positive because it is the current basically flowing on the, and here is the current of the diode, and the current of the primary is the same of the current of the secondary, besides the turning ratio, but basically the same. So the thing is that you never go in the other quadrants, okay? And you can verify it with this. If you do increase the LG, you will have more and more current before saturation. If you put LG equal to 0.001, you will have, as you can see, more and more currents before saturation. So you have to put a very high stimulus here, like 10 amps, in order to saturate. As you can see, I have to arrive at least 10 amps to saturate the current here. I repeat, I want to put the current I1 because it has more I of I1, because okay, as you can see, it has more meaning for me. So at 5 amps I saturate. If I do decrease the LZ, even with one order, this decrease dramatically. Even after 1 amp, I do have the saturation immediately. Okay, so it is reasonable to say that this belongs to, and the other belongs instead to the full bridge configuration. The full bridge configuration, if I write here full bridge, yes, something like that. I do run the simulation. Stop right there. As you can see, the voltage of the primary is between minus Vin and plus Vin, and the primary current of this transformer. Oh, sorry, we are still in the transit. The primary current goes between minus 2 amps and 2 amps. So the secondary is indeed the full bridge configuration. Now connect the correct behavior and describe the possible causes and solutions. So for this, I think that we need to understand what causes this in the first place. The first is the normal. So let's take this to this. The second instead is flux imbalance. And why you can say that? The flux imbalance is mainly given by an increment of maximum and a diminishing of the minimum, because we can have basically the first asymmetry of applied voltage or polarity, and second, we can have high ripple or partial saturation. And because the true saturation is given by this is the complete saturation, and I am positive because of this. You can understand that because when saturation occurs, so when sat happens, the inductor L diminishes a lot. You do remember in the other graphs that the graph of the L is like this, okay? If L decreases a lot, it becomes basically a wire, and so the current goes up exponentially like this. And you can also search on Google this. Just write saturation transformer waveform full bridge. I don't know. You should find. Oh, okay. As you can see, something like this. Not only this. Yes. This is an example. Yes, this is a good example. Yes, this is exactly what I was looking for. This is the transformer saturation because it is becoming more and more similar to a wire. And so yeah, you do have your answer. Okay, the solutions of course are better magnetic design, better core design, better everything. Okay, let's not waste time here. Isolated topology know-how. So here we have to understand what these guys are. Okay, so this is a push-pull, and of course I could open Spice in a minute and simulate the push-pull. Maybe I have already a push-pull here. Okay, I do have. I do have a push-pull already done. So we can do run the simulation and discover everything together. But let's think that we have in an interview and you cannot reason in any way. So what is the transfer function of this? Well, basically, push-pull, also full bridge and half bridge have all the same transfer function. Okay. Basically, they always have ns of mp times Vin times VO times D because the back is equal to VO equal to D times Vin. But then we have to add also the turn ratio, and basically it is the same. The rectifier plays no role in your transfer function. This gives you an S of MP, and that's it basically. These two switches are to drive the transformer, but basically it's a buck. Okay, nothing more, nothing less. If it is a buck in a synchronous configuration, well, this is the PWM1 and PWM2, and of course these are the switches. Q1 and Q2. Let me reason for a moment. I think that this is Q1, IQ1, and IQ2 because of course this is the gate. When the gate is on, the current is on. If it is true, then if it is true, so if it is the one, then I expect that this is also is 1. Because when the current is on, the VDS is 0. This is important. You cannot have this instead because otherwise you would have a dissipation which is disastrous, okay? So this is the VDS, and right in the green box the voltage stress. In a push-pull configuration, the voltage stress is given by 2V in. I suggest that you memorize at least the voltage stresses in the configuration like full bridge, push-pull, forward, and etc. Because it's quite useful, okay? Remember that push-pull configuration has 2V in and full bridge, because they have the body diode, they have just V in as stress. I think that you can find on Google tables of if you write tables of MOSFET stresses for isolated topologies. I think that you can find some sort of tables which indicate the stresses of. I think that you can find it because they are very famous. Okay, these tables. It's very. Yes, something like that. I think that you can find something on the net. Okay, you can find I will give it to you. I will give. By the way, I will give it to you something at the end of the video, maybe in the comments. I will give you the also these remember also these the selected topologies when you have to select what power topology you should select when you have something volts or okay, this is also important that they can ask you also this. So this is also the VDS, and this is of course the primary current, I primary, I primary. Okay. No 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 no, sorry 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 sorry, this is the VDS, yes, but yes, this is the VDS, but no 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 no, sorry sorry, these are the secondary current. This is the inductor current IL, but these two guys are the secondary current. And now you can verify everything in the LTspice simulation. I'm sorry, the duty cycle is wrong. It must be 0.5 and the parameter the 100 nanosecond. Okay, so let me do it again. This is another simulation, by the way, so I didn't even check if it is correct or whatever. Okay, let me just close this. Okay, the waveform are not so good, but I think that they are very very similar to the what I said. So the secondary side. And let's see the VDS of this. Whoa, they do behave horribly. They do behave horribly. Okay. I cannot even understand in this simulation what effectively they are. But yes, they are. Let's just say that they are similar to what I expect. You see that there is the interval here. There is very big resonance, but uh, it is like this. And last, the question: which converter does this waveform belongs to? Okay, let's answer also to this in a paint. So I think that these are both either full bridge or half bridge. And yes, the differentiation is basically to this. Vin, half Vin minus Vin, and Vin minus Vin. VP is the primary voltage across the transformer. And so this is a full bridge, because full bridge has this waveform between Vin and minus Vin. And the half bridge, since there is the capacitor divider here, attached to this point here, to Vin over 2, you will have plus minus Vin over the transformer. Vin half, sorry, over the transformer. You can verify it immediately with LTspice, just to go to the full bridge. The primary voltage, as you can see here, is between minus, and delete everything. But I can replicate immediately all this way from here. So get the gates, let's keep the gate V primary, VDS, I primary. Let's put, so let's delete everything. Delete. So these are the gates, VH, VB. This is the primary voltage. Let me put a very high dead time so that you can see it. Okay. Just for graphical purposes, I put a very high dead time. Okay, so now you can see it. Okay, so now it is very, very visible. So I primary, let's put the plot of I primary. Okay, so now you can see very clearly that it is identical to the very identical to what it is reported on the graph. And let's also put ID1, which is this. Okay, so it is identical. Let me do a screen here. So the first is the second is a full bridge. You can see the LTspice simulation. And the third, the first, sorry, it's an half bridge. So if I write here half bridge, I surely will have an half bridge in my electronics, in my spice. Don't know why I put this guy over here, I don't know, honestly. Maybe not an attempt to. Yes, there is no the time, so I don't like it. I don't like it. Maybe this is a very odd simulation. But anyway, even though it's even though the simulation is wrong, probably very wrong, you can see that you have the primary voltage between. No. It's a very old simulation, so I have to do by scratch. I can do it by simply by opening a new scratch, making something like this. Very easy. The secondary remains the same. Ah, sorry, this was the correct. Okay, so this was the correct half bridge. Sorry, guys. I have already done it. Okay, better. 0.5, T-dead. Let's put one MOSFET and let's cancel this useless thing. Okay, that I think that it is good for a full for an half bridge. The chance it is maybe a little bit too high, so let's put just 2 milli, and I think that we are good to go. So let's check the primary voltage, VP1, VP2. Whoa, what's with the oscillation? I don't understand, but anyway, let's increase the stop time to 10 milli. So as you can see, the V-in is 200 volts. So you expect that the transformer has a voltage between plus and minus 100 after this oscillation is finished. For some reason, I do have some oscillation. Ah, yes, of course I do have it because the output capacitor is so low. Oh my god. The output capacitor is so low that I have this oscillation here. But by the way, so I do have minus 100 and plus 100. So this is an half bridge configuration. And the primary current is something like this. Let's increase the. So by the way, the video, we can finish the video here. You have the perfect waveform here for the full bridge. The half bridge are basically the same, what just with the plus minus gain over 2. And I feel that this was an hard level interview. Hope that you enjoyed. Because now it makes, honestly, now it makes much more sense. Okay, guys, thanks for have watched this video. See you on the next one. Bye bye.